All right, AP Chemistry. This will be the notes starting the unit on what is commonly called redox or commonly called electrochemistry. This will be pages 83 through 85. I have a note here to talk about lab number 3. This is lab number 3 from last year. And it had to do where you took a beaker and in it you put a solution of copper 2 chloride dissolved it in water, or you dissolve the solid in water to make the solution, and then you put 2 nails in it. And so you stick a nail in there, another nail in there, which were mainly made of iron. There are a few other things in there, but it's iron that we care about. A reaction happened, and the point of this lab was that we looked, in first year chemistry, we looked at the moles of iron that reacted and the moles of copper. The point had nothing to do with the particular reaction, had nothing to do with today's lesson. It was all about moles. But it turns out there was a lot more going on at the time that we didn't want to talk about. So try to remember that lab. We'll talk about it more in class and why it relates to today's lesson. If you have your first year lab, go back and find it and take a look at it so you remember what it is. It'll help you understand and get something out of the discussion that we'll have in class. But I don't want to dwell on that. Let's jump into the main stuff. So you've probably heard the term oxidation before. Often if something is rusting or if it tarnishes, people will say, oh, that's oxidation or that's being oxidized. And they're partially right. Yes, it is being oxidized, but it also has a other half that we need to talk about, which is called reduction. But let's start with oxidation. It is defined as the loss of electrons. Now, this isn't necessarily the same thing as ionization, so be careful there. I can see why you might mess that up. It'll make more sense when we finish the whole picture here. And the way we show this is when we write an equation, we put the electrons on the right side of the equation. So I've got zinc neutral here. I've got zinc +2 here. The only way it can go from neutral to +2 is to lose 2 electrons, and they are placed right here. It doesn't matter what order you write them as long as the electrons are on the right half of the 2 sides. Let me rephrase that. The electrons have to be on the right side. Now, let me talk about a half equation. A half equation suggests that there's a other half, and there is another half. It is the half that is gaining the electrons, and we're not looking at that right now. We're just looking at who is losing. You might also notice the state change. Zinc neutral is a solid, where zinc +2 is typically aqueous, and that's something you'll see a lot of. Oxidation number. At first, oxidation number looks like the same thing as the ion charge. So for example, right here, zinc +2 has a charge of +2. It also has an oxidation number of +2. Zinc over here on the left has a charge of 0, and it has an oxidation number of 0. So in many cases, the oxidation number is the same as an ion charge, but things have an oxidation number even if they don't have a charge. So let's go through the steps. I'll show you where that comes from. So it's the measured charge carried by an atom, whether it's an ion or not. And you want to go through these rules in order once we get to right here. That's going to be important. So if something is an elementary substance, like these 3 here, Cl2 neutral, sodium neutral, iron neutral, and like we had up here, zinc neutral, its oxidation number is 0. If you have a single atom, monoatomic, and it is an ion, that is its charge. So an example would be what we saw above, the thing with the zinc. So zinc plus 2, it would have an oxidation number of 2 plus 2, and it also has a charge of plus 2. Now, when you have combos of atoms, this is where things get a little bit complicated. Follow this order when assigning them, because certain things are more insistent on having a particular oxidation number than other things. And it's no surprise that group 1 is a bit picky. Group 1 really likes +1 because that extra electron in the s orbital, it doesn't really want that electron very much. And there's a good chance there's another atom in the group that prefers to have it, so you can think of that electron as going to the other atom, which is why group 1 is typically +1. Group 2 likewise is +2. Fluorine is usually -1 because fluorine wants to have an extra electron. It is short 1 electron from an octet. So it makes sense if you had something like NaF. The sodium would be an oxidation number of +1. Fluorine would be -1 because that extra s electron from the sodium doesn't really want it, and the fluorine does really want it, and so that should make sense. Hydrogen is +1 because having only 1 proton, it's hard to hold on to your electrons, and oxygen is -2. After that, you can just figure it out using math. Step 4, the sum of all oxidation numbers in a molecule or ionic compound is 0. In other words, if the whole group has no charge, like NaF, overall, it doesn't have a charge. The oxidation numbers have to add up to 0. However, if the group is a polyatomic ion, then it needs to add up to the charge of that ion. So like here, sulfate. The oxidation number of sulfur and all 4 oxygens must add up to -2. So here's how we figure out the oxidation numbers. We start with the chart. Well, oxygen's in the chart. So, okay, oxygen's -2. And then you think about it. There are 4, let me write this again, show you how I write it. There are 4 oxygens. That combo of 4 oxygens, if each of them is a -2, is -8. So you have to think, what must the sulfur be so that when it's added to these 4 oxygens, we have a total of -2. We have to end at -2. Well, of course, it ends up being a +6. +6 minus 8 is a total of -2. And make sure you account for all 4 oxygens having a -2 oxidation number. Bigger groups start to get more complicated. So if we take a look at sodium dichromate, again, go through the list in order. Sodium's +1, oxygen's -2, and you have to look at how many there are. There are 2 sodiums, so that's a total of +2. There are 7 oxygens, so that's a total of -14, and the overall group is a 0. So you have to think, what must the chromium be? Well, 14, -14 plus 2. Okay, now we're at -12. But the -12 is going to represent both chromiums. And so you have to think, well, what must each chromium be? Well, that means that each chromium must be, excuse me, let me rewrite that. That did not turn out the way I intended. We have a -12 from the sodium and the oxygen. We need the chromium to cancel it, so the chromium, both of them must be +12. That's how I intended that. So each chromium must be +6. That's why I get the +6. There. As we do this section on electrochem, you'll see there are certain atoms that can have a variety of oxidation numbers. Chromium is one of them. You'll see chromium a lot with different numbers. You'll also see manganese. Those are two very common ones. I'm trying to think of some others right now. Other cobalt. They have a bunch of different values. You'll see iron sometimes because it has 3 common values. Let's see, other ones, copper. Those are some common things that you'll see with different numbers. Let's look at one that's a little less expected here. In the case of water, we go through the list, hydrogen's +1, no surprise. And oxygen ends up being -2, no surprise, and it works out. But if you look at H2O2, hydrogen peroxide, think about the name, peroxide, that's telling us there's something special with the oxygen. Otherwise, it would just be called hydrogen oxide like water. Well, hydrogen's +1. And notice, if the 2 hydrogens make a total of +2, there are only 2 oxygens. And we need both, I don't want the eraser, both oxygens to be a total of -2 because the overall group, H2O2, is a 0. So if 2 oxygens have a total oxidation number of -2, each oxygen must be -1, which looks weird, but that is the case. It turns out the oxygens would prefer to have more electrons, they're just not available. So that's the best it can do. Now we have to look at the opposite direction. We did oxidation, which is the loss of electrons. Now we got to look at its other half, who is gaining electrons. Yeah, just go ahead and show the rest of this page. I think it'll be easiest. And this is called reduction. Now it's called reduction because the oxidation number becomes more negative. You are reducing the oxidation number because you're gaining electrons, and electrons are negative. So it's a little bit counterintuitive. You're gaining something, but you're becoming more negative because it's electrons. To show this, we put them on the left side. So you can ignore this. We'll get to that in class. If we take copper +2 and we gain 2 electrons, we become copper neutral. Again, that copper here would be an oxidation number of +2. Here it has an oxidation number of 0, and it is gaining 2 electrons. Notice again, the ion is aqueous, the neutral metal is solid, because that's how they exist. Now you can't have one of these without the other. You have to have oxidation and reduction happening at the same time. So reduction, oxidation must happen. You can't have somebody gain 2 electrons unless somebody loses 2. So if I take that example earlier, we could combine the 2 and we could say this half is gaining. And if I grab the half from the very beginning of the notes, way up here with the zinc, I could say that zinc is losing 2. And this would make a very satisfying pair. And each of these is called a half equation because it's half of the complete picture. And you typically see these when doing these types of reactions where somebody is losing electrons and somebody is gaining. Now, because these always occur together, they're typically referred to as redox, reduction oxidation reactions. And that's why this whole unit is often just called redox, because that's what we're going to be looking at. Now, I mentioned a phrase that might have caught your attention up here. Leo says grr. That's just a corny way to remember who is gaining and who is losing. So Leo, lose electrons, oxidation. The lion says, grr, gain electrons, reduction. And to be honest, I still say it in my head when I'm doing these problems to help me get it straight. Or I think about why the term reduction is called reduction, but that takes too long. Leo, the lion says grr is more fun. There are other ones. Some people like oil rig. Oxidation is loss, reduction is gain, but that's not as much fun. That's the only ones I can think of right now. So we're going to go with Leo. That's more fun. Typically, I like to ask this: what reaction have we studied that is always redox? And the answer is combustion. I can't think of a combustion reaction that isn't also redox. We'll go through that in class as to why. See if you can figure it out. Take a combustion reaction like CH4 burning, so react it with O2 to form CO2 and water, and see if you can figure out why it is redox. And then there's another set of reactions that's never redox, and that's precipitates. Precipitates, nobody is changing their charge or their oxidation number. They're either just dissolving or the ions are sticking together. And so maybe test yourself on this one too. Do the classic precipitate when you have a solution of, let's say, silver nitrate mixed with a solution of sodium chloride. First, see if you can remember who the precipitate is, and then write it out as ions and see if you can see why it is not a redox reaction. It'll be good practice. All right, balancing redox equations. This is, it's one of those big steps in your education in chemistry. This is one of the big defining moments between first year and AP. It gets a little messy because what we have to do is we have to balance the atoms, like always. We can't break the conservation of mass. And we also have to balance the electrons. And what I mean by that is, if somebody is gaining 5 electrons, somebody must be losing exactly 5. You can't have somebody gaining 5 if somebody else is only losing 3. So we're going to have to look at the electrons as well. And there are different ways of approaching. I have found this 5-step method to be a good starting point. And I encourage you to do it this way, doing all 5 steps at first. And then once you get comfortable, you can collapse it. I'm at the point where I usually can do it as either a single step or maybe 2 steps if it gets messy. But I do encourage you to start doing all 5 steps and actually label them like I have here. You'll see in this first problem, I actually labeled 1, 2, 3, 4, 5. Do that until you feel comfortable, which will probably be anywhere from 5 to 10 examples to go through, and then you'll get to the point where you don't need to do every single step. Well, let's go through them. First, split into your 2 half equations. One of them will be oxidation, one will be reduction. If you ever write your 2 half equations and you have 2 oxidations, you're wrong, and if you have 2 reductions, you're wrong. You have to be one of each. Then you get to actually add things sometimes depending on the solution. If it's neutral and water is needed, in other words, if you need hydrogen and oxygen, you can add water into the appropriate side of your half equation. If it's an acidic solution, you can add water and or H+. It's hard to read, but that's H+ right there. And likewise, if it's basic, you can add water and or hydroxide. Sometimes you don't need to add anything, and sometimes you do. It's because you don't see it in the overall reaction. You only see it when you're looking at just the half. And in step 2, I kind of skipped it, you're balancing the atoms like usual. So you've got your 2 halves and you balance your atoms like usual. Now in step 3, we'll start looking at electrons. Make sure that the number of electrons gained and lost is equal. If it is, automatically, you're lucky and you're done. If it isn't, you're going to have to make some adjustments. And then step 5, you just add everything up, cancel things that are on opposite sides of the arrow. And it's a good idea to check your electrons to make sure that the number gained and lost are equal. So let's go through some examples here. All right, the only reason this has meaning, the neutral, it just means the only thing we can add is water, but it turns out we don't even need it in this case. Splitting the overall reaction into the half is often where I find students have the biggest problem. Where you want to start is just start with similar atoms. So we're going to pull the chromium out as 1/2, and we'll pull the chlorine out as the other half. It's not always that obvious, but that's a good starting point. So in step 1 here, I've got my chromium half and I've got my chlorine half. Notice I didn't worry about electrons yet. I didn't worry about balancing the atoms. I'm simply just identifying my two halves. In step 2, now I'm balancing my atoms. My chromiums were already good, but I needed to put a 2 here to balance the chlorines. Step 3, now we're going to look at electrons. In order for chromium to go from +3 to 0, it's just not shown, it needs to gain 3 electrons. And again, if you're struggling with the whole gaining of electrons, losing of electrons things, remember, there's always this battle between protons and electrons. If they're equal, it's neutral. But if you have extra protons, it's positive. If you have extra electrons, it's negative. So in the case of this chromium +3, it has 3 more protons than it does electrons. But if it gains 3 electrons, now they'll be equal and it will be neutral. And what you can do if you really need to help you with this is you can write it out. You can say chromium +3. What is chromium? Where's my period? I think I have a periodic table in here somewhere. Actually, there'll be one right here. This isn't where I intended. Oh, that's not what, that's, no, those are answers. Oh boy. There it is. I knew I had one handy. Chromium is element 24. So you can say it's got 24 protons, and since it's +3, it's got 21 electrons. We know that it's becoming neutral, which means it's got 24 protons and 24 electrons. That means the only way it can make this change is to gain 3 electrons, which we show like that. You may be slow at first, but you'll pick up speed on that probably by the end of this lesson. Chlorine, it's going from -1 to neutral, so it's losing electrons. And notice each chlorine is losing 1 electron, but there are 2 chlorines in the discussion. So even though each chlorine is only losing 1 electron, there are 2 of them doing it. So as written, there are 2 electrons being lost. That is a common mistake people make, is they think, oh, chlorine's only losing 1 electron, and they write 1 electron here. They don't factor in that there's already a 2 in front of the chlorines. That's why you have to balance your atoms first. I labeled this chromium as being reduced, and the chlorine is being oxidized. That's just for practice. You don't have to label that when you're doing the balancing unless you're asked to. It's just something to practice since we're just learning this. Now, I'm going to tidy this up a little bit. If chromium's going to gain 3 and chlorine's only going to lose 2, this doesn't work. So we need to find a common number that they both will fit into. That, of course, is 6. So I'm going to multiply my entire chromium half by 2, my entire chlorine half by 3, and you multiply everything in there, and you end up with what I have in step 4. And what I've done in step 4 is I've now gotten my electrons equal. I've got 6 here, being gained and 6 here being lost. At this point, you're essentially done. You just check it, add everybody together. The electrons cancel in the overall reaction. So what's interesting is the whole point right now is electrons being gained and lost. Yet, if you look at the overall reaction, you don't see it. It's hidden. It's happening, but you don't see it unless you look at the halves. And you just add all the atoms on their correct side. Nothing else cancels in this particular case. And it works out like this. One thing you can do at the end is you can do a check. You can add up your total charge on the left and your total charge on the right, and they better be equal. Notice 2 times plus 3 is plus 6. 6 times minus 1 is minus 6. So this side is a total of 0, and the right side is already 0. And so that's a good way to check to make sure that it worked. If those don't match, then you made an error somewhere. All right, now let's do this one, which is going to be acidic. And again, all that means to me right now is that if I need to, I can add H plus and or water. All right, first we have to split into our 2 halves. So I've got manganese here and manganese here. That O4, just take it along for the ride. That creates 1 half. My other half will be the iron and the iron. So step 1, I have my 2 halves identified. Step 2, balance the atoms. Okay, well, M and NO4, I said that funny, is becoming Mn plus 2. But I don't have any oxygens on the right side of my equation up here, so I have to add them. The only chemical I can add that has oxygen is water, and to get 4 of them, I add 4 waters. That gives me 4 oxygens. But now, that is added hydrogen to my equation. And there's no hydrogens on the left. So there are 8 hydrogens right here. So I need to put 8 hydrogens on the left as 8H plus. And again, I can only add H plus exactly like that and or H2O. So that's why, again, in order, I started with this and this, which we had from step 1. I then realized I needed some oxygen, so I added the 4 waters, which then caused me to have to add the 8H plus. The iron atoms are balanced, so that's great. Okay, now step 3, we need to start looking at electrons and whether they're gaining or losing and how many. Let's do the iron first, it's easier. It's going from plus 2 to plus 3. Okay, look at it this way. If iron plus 2 gained electrons, it would go from plus 2 to plus 1 to neutral. So it's not gaining, it's got to be losing. And it went from plus 2 to plus 3, so it's losing 1 electron. Again, you can write out iron plus 2 and iron plus 3, and you can list the protons and list the electrons and see how it all works out if you need to do that. I'm not going to do that right now. This other one's a little trickier. To remind you, MnO4 minus 1 is the polyatomic ion per manganate. And in this case, MnO4 with a minus 1 charge, well, according to the oxidation numbers, this is a total of minus 8. We need to end with a minus 1, so that means the manganese must be plus 7. That one might take a little practice to get used to. And I like to do this when I'm doing the problems. I'll write the charge above the atom. So I'll write a plus 7 right there above that. Mn plus 2 is plus 2. Well, to go from plus 7 to plus 2, you have to gain 5 electrons. Right there. Okay, our electrons aren't equal. We've got somebody gaining 5, but somebody only losing 1. Well, it's an easy fix. All I have to do is multiply the iron half by 5, which gives me this. 5 iron plus 2, 5 iron plus 3, 5 electrons. And so now in the end, I am adding this equation. I just didn't bother rewriting it. And my modified iron equation. As always, the electrons will cancel. Add everybody up, cancel anybody that's on opposite sides. In this case, it's just the iron. It ends up looking pretty messy down here. I mean, this starts looking complicated, but that's just how it is. And after you add it all up, you can do a check. In your left should be a total of plus 17, and your right will be a total of plus 17. So that's a safety check that it did work. Now, just for the sake of discussion, let's say that in my half equations, I had 8H plus right here, which I do. And let's just say for some reason in my iron half, I had plus 2H plus. So let's just look at that for a moment. That I have 2H plus here, and I'm just making this up as an example on that 8H plus. What you do is you would cancel these two, and you would have 6H plus on the left. That happens sometimes. It might even happen in the next example. I don't remember. All right, next one. Basic solutions can be a big old pain. Sometimes you'll do one that's basic and it'll all fall into place. No big deal. And other times you just are stuck and have the hardest time balancing it. So I usually avoid these on exams because they just take too much time. In this case, I have a couple of hints. When you're balancing your atoms, if you have to add waters or hydroxide, it usually works out best to add waters to the side that has extra oxygen. Sorry, that's a little blurry. Or if you already have hydroxide, doubling the hydroxide sometimes works. There's a few other tricks, but these two I find usually works. Now, the problem that can happen is if you put water on the wrong side, you'll put water, and then you'll have to put hydroxide on the other side, and then you'll have to put more waters and more hydroxide, and you end up in what I call a balancing pickle. So if you end up in that, where you just keep raising your numbers and you're in this endless loop, that means you've got water on the wrong side of your equation. Go back and try it on the other side. So here are my two halves. I've balanced my atoms. In this case, I ended up putting 2 waters on the left here, 4 hydroxides here, so that I have a total of what? 6 oxygens on the left, 6 oxygens on the right, and 4 hydrogens on both sides. I then figured out that the left side is, for the top reaction, is gaining 3 electrons. The bottom is losing 2, so I'm going to double the permanganate half, and I'm going to triple the iodide half. That leads me to step 4. My electrons cancel, and everything else adds up. Again, sometimes these get a little weird, so in your homework, don't be surprised if some throw you for a loop. Think of them as a challenge problem. Now, in this section, we have something called agents. And agents, you are an agent that causes something to happen to something else. That was not a good way of explaining it. Let me re-say it. Whatever is happening to you, you are an agent of the opposite thing. So if you are being reduced, you are an oxidizing agent because you're causing somebody else to be oxidized. And likewise, if you are being oxidized, you are a reducing agent because you're causing somebody else to be reduced. This will make more sense when we look at one. Take this equation here. It's already been balanced. You need to focus on the atoms that are changing oxidation number. So notice hydrogen and oxygen are not changing, so we don't care about those. It's the chlorine and the nitrogen. The chlorine right here is -1 oxidation number, and right here is 0. So it's going from -1 to 0. It is being oxidized. Leo, it's losing electrons. So the chemical that the Cl is in, which is here, is called the reducing agent. So HCl is the reducing agent. It's the Cl minus 1 that is being, but it's the chemical that the Cl is in that is the reducing agent. And it's always referring to, well, usually it's referring to reactants. The nitrogen here is +5 if you go through the steps, and here is +4. And it is being reduced. So the chemical that the nitrogen is in originally, nitric acid, is the oxidizing agent. So what you do is you figure out what something is undergoing and just say it's the opposite agent. We'll practice that. Here's another one. Chromium is going from +3 to 0. Gaining, reduced. It's an oxidizing agent. As soon as you figure out what one chemical is doing, if there's only one other chemical, it has to be the opposite thing. So even without looking at this, if this is the oxidizing agent, the aluminum must be the reducing agent, but we can, of course, go back and verify it. The aluminum is indeed going from 0 to +3. That is losing electrons, Leo, oxidized, so it's the reducing agent. Little review here. What is reduction? The gain of electrons. Oxidation, the loss of electrons. Can one happen alone? No, you have to have both together. You can talk about one of them alone, but you can only really do it with them happening at the same time. And my note here about lab 3, we'll talk about that in class. But again, please do look at lab 3 if you have it. If you don't have it, find somebody who does. It's a good lab to review, not only for what its intended purpose was, but mainly for right now, the redox reaction that was happening, which is actually a lot more interesting than the moles that we use it for. It wouldn't hurt to do the lab again if we had time, but of course right now we don't have a lot of time. And that does it for this lesson.